hope that you will take away something that may not be directly related to your department, but is what's happening outside your door. My background is in environmental infection prevention. I work in the environment with the environmental support services workers. My background in research was at UCLH, where we developed a lot of initiatives, researched a lot, but never actually put a lot together as process and protocols. We unashamedly looked at the food industry. They did lots of things well when it came to cleaning and decontamination and hygiene. So we looked closely at what they did use and use successfully and looked at ways in which we can implement that in the healthcare environment. And this is an output from that particular notion of work. Now that I've put that theme in your head, that wasn't intentional. I was at a conference recently for infection prevention and control, and Dr. Mike Weinbrenn said that this particular subject matter was impossible to resolve. Now, at the time, I knew what the food industry was doing. I didn't say anything at conference, but we've named this project Mission Impossible. The risk factors associated with drains and taps was really highlighted with recent publications coming out of Netherlands and Germany. And the result of that work is actually removing hand wash basins from intensive care units. Now that really bothered me. It bothered a lot of infection control professionals, and we're saying, are we destroying the culture of hand hygiene as a cornerstone of infection prevention and patient safety? We spent the last 20 years trying to get people to follow the process, the 5 moments of hand hygiene, and make hand hygiene available to them. Hand washing is an important part of that. So it started off a train of thought. I'll park that political and cultural thing to one side. We said, okay, can we fix this? Is there a way in which we can engineer out the problems of biofilm occurring in films in the environment? And I'm sure that you understand biofilms probably better than I. But what we did learn was the fact that the drainage system, and this is a piece of work that's just recently come out from Ireland, which really highlights the impact that where you have a drainage system, it is all linked. It's one colony, one community that you have to deal with. The drain network is inaccessible. Sorry, I'll move these on. I'll just highlight those. We create dams and reservoirs within the actual links themselves when you start to look at how these are formed, and these are quite complex. The biofilm matrix itself is very resilient. It's complex and has a diversity of organisms in there. And our concern about this is multiple drug resistance. These guys are very sociable, and they will share genetic information, and that's where we're starting to see the risk factor of dispersion from a sink out into the environment, onto a healthcare worker, onto their hands, onto their uniform, of a multi-drug resistant organism in an intensive care unit. So the proximity and density of the actual organisms within the biofilm allow for this antimicrobial genetic transfer. And obviously there are concern about droplet dispersion and aerosols. This is a study I was referring to. It was published recently in the Journal of Hospital Infection and is from the University Hospital Limerick. They had the wonderful opportunity, as I did, to take a department apart when it's been decommissioned. And so they've actually taken 20 of the pipe sections from the various parts of that unit that's been decommissioned to analyze the biofilm that's contained within the pipework. All of it was contaminated, and it was common to the healthcare-associated infection research and tracing back on the genetic genome of the infection that was there. So this was direct proof of the impact on the actual patient on infection. So the issue now is, okay, we have a hierarchy of controls. Do we potentially have the opportunity to remove the source, or as per, let's get rid of the sink and the infections will stop? But the other problem is, how do we wash our hands, or how do we make hand washing available conveniently? Or do we mitigate the critical risk factors by engineering out a process? So I talk about sink use and abuse. There's a nice piece of work that shows how sinks are used. Most people do use them for hand washing, but they use them for multiple other activities, anything that's liquid or desirable to go down a sink will. And that's the problem of human nature in terms of disposal. So we're actually feeding the sinks. And this is the problem with feed and nutrition from patients going down through into the sink area. We know that chemical treatments have a limited zone of effect. So if you're pouring a chemical down into the area, you're simply putting a liquid, it's going to seep to the bottom. So you're only dealing with any biofilm or contaminant at the bottom of the actual pipework. The biofilm itself is completely around inside the pipe. Even if you're using a foaming agent where you're actually getting that radial approach, it's not penetrating sufficiently in there and eventually will grow back. So now we're looking at potentially a daily cycle of decontamination of sinks, and we're trying to address some of the green issues of the reduction of chemicals. Part of our work at UCL was say, how do we work with nature rather than against it? These organisms are smarter than we, and they will always kick back because we don't have a complete solution. The complete solution is to work with nature, preferably using nature's own tools to balance the environment. Excuse me. Typically, the drains are inaccessible. One of the risk assessment when we looked at how this was being used in the food industry, and this was biofilm within food chillers, food refrigeration, is the pipes that carried the condensate from the chiller were being filled, and then you start to see the leaks, and I'm sure we've all seen them in the supermarkets. That potentially has a problem of food spoilage and, at worst case, illness caused by the contamination of the actual food itself. So we have to look at ways in which we can actually address the drain, but we have to contain it in whatever we're doing. And that requires containment at the point of entry by the methodology that we're going to employ. And we need to look at where we're pushing this contamination to. A drain goes out. That's the way that we would actually work, from the point of entry to the out and exit of there. The strategy was really all about biofilm removal. It can't be a chemical solution. It has to be physical removal. And ideally, we want to leave that process where we're inhibiting further recontamination for as long as is possible. And this is the part of the work that's incomplete at the moment, as we're going through peer review and operational trials to look at the levels of recontamination of those drains after the intervention. And obviously, we need to develop the methodology and tying into that the frequency of cleaning, very much similar to steam cleaning of sanitary areas, for example, that when we introduce steam cleaning into, periodically deep cleaning into sanitary areas, this will be a similar sorts of process. So it's something that would be a work around between estates and environmental support services, our housekeeping staff. This is the approach. It's a probe that has the ability to run and enter into the drain system. Unfortunately, when you look at a drain system, it's multiple bends, curves, joints that there, so actually access is quite difficult unless you've got something that can migrate through all of that environment. As I mentioned earlier, containment is very important. We need to maintain control over droplet dispersion and aerosolization at the point of source, at the point that we're actually entering. We need to look at cleaning, so we have mechanical pressure to flush out the majority of the soil that's existing there, and then look at the decontamination process. And this is where we use saturated steam to emulsify, pasteurize the fats and the materials inside it, and this happens in a halo effect, so it's not just sitting on the bottom, it's actually completely around the whole interior of the drainage system. And then look at protection of an antimicrobial surface treatment, which is a covalent bond to the actual material itself. It's not a disinfectant or a chemical that's going to go down the drain. This is actually going to bind to the actual drainage plastics or materials itself and give us inhibitory effect. Sort of a biostatic approach. And then look at our environmental sustainability, as I say, reduced chemical usage in disinfection and decontamination, and making sure that we are compatible with a water-based process. So this is what we're dealing with, is the original bottle trap here. This is a sludge pond. That's where all of the the biofilm collects, or the P-trap, again, which is moving through into the main drainage areas. So these are old-fashioned forms of drainage which are promoting the location of biofilm. Again, looking at a standard waste pipe connection is you've got these pieces not necessarily joined together inside. You've got this area, ridges where the actual interior surface irregularities are desirable for harboring and setting up the organisms. So this is the study where it was actually the pipes were all taken apart and actually analyzed, and say all of the biofilm was consistent throughout the whole organization, throughout the whole ward area. And the linking in of any room, if you've got contamination going into one, it will spread through the whole system. The actual trap itself is an important element of design, and this is again looking across to translate information from other areas. This is a design improvement that's looking at waterless urinals, so that the actual water itself will release and go down, but prevent anything coming back, including odor. So by adapting to this, you can actually eliminate the bottle trap and the P-trap and use this as the point of entry into the system. The actual collar here, the neoprene valve, will open with 2 mil of water, and after flow will immediately close and prevent anything coming through. So this becomes a point of entry for the probe to actually enter into the drainage system. This is the unit itself. This is part of the prototype of risk assessment for use in healthcare, together with this actual sleeve that goes over the top. We were looking at eliminating cross-contamination between different project work, and that this actually here contains a disinfectant approach. So we're actually feeding the probe back into this container. It's circular, so it's opening up the spring that this material is and moving in and disinfecting it, so it will actually come out ready for use, fully disinfected. And this is just how it's feeding into the actual unit. Going round, it's opening up the actual spring of the unit itself. Actually, I'll just move this further along. Okay. The antimicrobial protection is a silane technology. It's not a particularly new technology. Again, it was used extensively in the food industry, designed by Dow Corning in the United States to coat initially glass. It bonds permanently to a surface, so it does not leach out into the environment, or does it cause any antimicrobial resistance. It is a mechanical form of killing. It has a leg on there which actually penetrates any organism and renders it completely dull. So, mission impossible. We think we've solved it. We're moving ahead, as I say, with peer review to look at it and to evaluate the actual process of the use of it. In terms of our only doubt at the moment is being able to determine the frequency based on the actual usage of the sinks themselves. Use and abuse. If we use it for hand washing, this will work very well with very good extended frequency of treatment. If we're continuing to abuse sinks and pour other things down which promote biofilm formation, then that frequency would have to adjust accordingly. So should you wish to accept the challenge, I'd be very happy to work with you on that. Thank you very much.